All right, it's just a little bit past 45 after the hour, so let's go ahead and get started. Welcome to the third NOAA AI workshop, session 11B on AI for the blue economy. My name is Benjamin Richards from the NOAA Pacific Islands Fisheries Science Center, and I'll be co-hosting this session with Jordan Watson from the Alaska Fisheries Science Center. Today we have 5 exciting talks covering various aspects of artificial intelligence as it relates to acoustics, autonomous vehicles, ocean circulation patterns, Arctic seals, and even the inner ear bones of fish. So a lot of exciting material today. I have a few housekeeping details while Irina, our first speaker, queues up her slides. The first is the code of conduct that I'm sure you've all seen. The NCAI is committed to providing participants of this workshop with a safe, productive, and inclusive environment. We encourage active but respectful discussion surrounding all aspects of the topics. Harassment of any kind or intimidation will not be tolerated. If you feel that you have or are experiencing any type of harassment, please email ai.workshop@noaa.gov and we will have that taken care of immediately. Anyone engaging in harassing behavior will be expunged from the meeting. Also, I will direct people to the Slack channel for AI and the Blue Economy. That's where we will be having the Q&A session for each of the talks. With that, let's go ahead and get started with Irina Benson from the Alaska Fisheries Science Center, who will be talking about AI as it relates to otoliths and fish aging. Go ahead and take it away, Irina.
Can you see my slides?
We can.
Okay. So, hello, my name is Irina Benson, and I'm here to present our work on Fourier transform near-infrared spectroscopy of otolith coupled with artificial intelligence to predict fish ages. Our lab is located in Alaska Fisheries Science Center in Seattle, Washington, but we study fish in Alaska. Fish age estimation is one of the costliest elements of integrated stock assessment in terms of both time and money, with demand for age data outpacing our capacity to deliver, innovative approaches are needed. So in 2019, NOAA Fisheries funded 5-year strategic initiative to improve age estimation efficiency using Fourier transform near-infrared spectroscopy. And we are trying to implement this technology all over the NOAA labs, all over the United States. Our objective was to explore advanced technologies using F10IR spectroscopy of northern rockfish, otoliths coupled with deep learning models to estimate fish age more rapidly and with greater efficiency than traditional approaches. In this presentation, I'll briefly go over study object, fish aging methods, and then deep learning models. For this particular project, we studied northern rockfish, and here on the right you will see northern rockfish and northern rockfish otolith picture. Otoliths are small calcified structure in the inner ear of fish, and we use otoliths to assess the age and growth rates of fish. So up to date, we collected over 56,000 specimens, yet we were able to age over 25,000 specimens. So you can see the problem. We need new technologies, and maximum age of northern rockfish, what we recorded, is 88 years, so it's a long-lived fish. Our traditional aging methods are validated, and here on the bottom of the slide, I'm showing a couple papers on age validation. For this project, we collected over 1,100 samples in the Gulf of Alaska. And in addition to otoliths, we also had access to geospatial data and biological data. Traditional aging methods involve a lot of steps. Here on the right, you'll see what first we have to examine otolith under the microscope, find the otolith core and draw a line through it, then cut it on a special saw and either burn it over open flame or in a special oven to enhance patterns. And only then you're ready to age fish. And for long-lived fish, it's very difficult. Here, it's relatively clear otolith, and you can see little blue dots. Each dot is 1 year of age of fish, and it can get very confusing. So new method is very promising. Here on the left, you see a spectrometer, and all you do is take otolith, put it on top of integrated sphere, cover with gold-coated stamp, push the button, and in less than a minute, you have a spectra ready. And the concept behind these instruments are pretty simple. You send certain amount of light to your sample and then collect reflected light, measure it, and from there you can calculate how much light got absorbed. And these instruments are built very solid. Here in this schematic, you'll see desiccant. It controls for humidity, laser to do internal calibration of the instrument, and then source is sending light to interferometer, which is equipped with cubed corner mirrors, and from there light goes to otolith, and reflected light gets collected in the integrated sphere and gets sent to detector. And since these instruments are non-sensitive to vibrations and temperature fluctuations, we are hoping to explore how to place these instruments on the fishing boats so you can actually detect age in real life. Molecular spectroscopy is the study of interaction of electromagnetic waves with matter. So otoliths are composed of alternating protein and mineral-rich bands. Molecular bonds and organic fractions are capable of rotation and vibration, which include bending and stretching. Overtones and combination of CH and H and OH molecular vibrations occur in the near-infrared part of electromagnetic spectrum. Molecular vibrations are measured over time and frequency domain and collapse to frequency domain. So now you get the spectra. And here on the right, you'll see northern rockfish spectra. It's actually spectra collected for this project, and it's colored by ages, and you can see the difference between younger and older ages. I'm going to show you a brief overview of how predicting fish age from otolith spectra actually work. You have the samples in the vials, in the boxes. You take a sample, you need to collect spectra and age. Once you get these two data sets, you can then build the calibration. You train the calibration model, you validate it, and once it's ready for production, you can load it into the instrument, and you're ready to send a known sample, scan it, and age is then now ready sent for assessment. Traditionally, we use traditional chemometrics models, which work great for shorter-lived species. For longer-lived species, we have an issue with nonlinearity. Plus, we really, for like partially square regression models, which we used here, we really need to be careful with using most informative regions of spectra. So a few months ago, we started exploring Google Cloud platform to increase our computational capabilities, and we got to work with Giovanni, who is a Google machine learning expert, and I think he may be even attending this talk. So he introduced us to this concept where we can fuse the spectral data with biological and geospatial data and send it through deep neural network. And in this particular study, we're looking at two different types of neural networks, deep neural networks and convolutional neural networks. We use TensorFlow to build these models, and then Bayesian optimization and hyperband Keras tuners to perform hyperparameter search. Neural networks are made up of layers of neurons, and neurons are core processing units of the network. Each data point fed as input to each neuron of the first layer. Inputs are multiplied by corresponding weights, and their sum is calculated. Then each of these neurons is associated with numerical value called bias, which is then added to input sum. Resulting value is then sent through the threshold function called the activation function, and this activation function determines the output. And also for our models here, we use two types of nonlinear activation functions. You can see the information on the right, red in yellow. This is the architecture of our deep neural network. We had 3 hidden layers, fully connected layers, and used dropout for regularization. And results are promising. DNN model handled nonlinearity in data better than our base model. And for this model, 93% of variation in the traditional microscopic ages can be explained by spectra from otoliths for both training and test data set. Also, 67% of the time we will predict the age relative to traditional age plus or minus 3 years for both training and test data sets. We also took a look at what factors in our data played the most important role in predicting fish ages. Based on factor important plots, otolith spectra in the 4,000 to 8,000 inverse centimeters wave number region, which is associated with CH and NH functional groups, had the highest influence on the model. Otolith weight, for which, you can see it right here, for which both fish age and somatic growth are determinants, had greater impact on fish length, and coordinates had impact due to fish ontogenetic habitat shifts. And Blend-Altman plots showing difference in average values of two methods, traditional microscopic methods and FTNR spectroscopy method. Age estimation outcomes between these methods were essentially equivalent. The average bias was close to zero, and 95% of the differences between the two ages methods were within a range of 6.5 years. We also took a look at convolutional neural network, and convolutional neural network models are great for image data, and you can think of spectra as one-dimensional image. So here we apply kernel or filter of certain size to our data and store dot product in an output array, and then activations of the kernels then fed forward in the neural network into pooling layer, and then to new convolutional layers, so standard dense layers. And purpose of a pooling layer is to shrink the input. Here you see architecture of our convolutional neural networks is just one deconvolutional layer, and then we, after pooling layer, we had the one dense layer. And results are also promising. For this model, 94% of variation in traditional microscopic ages can be explained by spectra from otoliths for training data and 89% for test data sets. Also, 67% of the time we will predict age relative to traditional age plus or minus 3.85 years for test data set. Blend-Altman plot is showing the bias close to zero, and 95% of the differences between two aging methods were within the range of 7.6 years. So in conclusion, FTNIR spectroscopy of otoliths coupled with deep machine learning definitely as promising methods to predict ages of long-lived fish more rapidly with greater efficiency and with comparable precision. Based on factor importance plots, otolith spectra in 4 to 8,000 inverse centimeter wave number region had highest influence on the model. Otolith weight and coordinates also had influence on the model. Deep learning models definitely handle nonlinearity in data better than partial least square regression models. And also based on Blend-Altman plots, FTNR spectroscopy of otoliths coupled with deep learning can predict fish age more with comparable precision to traditional methods. And to improve results, we definitely need to collect more data. So we are hoping to get more data for 2021, 2003 and beyond, and try other deep learning approaches like data augmentation for convolutional neural network. And I would like to acknowledge National Marine Fisheries Service Science Board for funding this our strategic initiative, and also say thank you to all Age and Growth program staff for collecting data. Giovanni Marchetti helping us to build our first deep learning model, and Jason Erickson, Melissa Sheff from Brooker, who always help us with instruments when we need them. And thank you.
Great, thank you very much, Irina. Fascinating talk. There's already a couple of questions in the Slack channel. So I'll just address one right quick while Kimberly is getting her slides ready. Can you discuss if and how your work might be applied to tropical species where the otolith annuli are much less distinct?
Well, that's actually, this technology may work great for this kind of otoliths because we're not relying on the visual analysis. As long as we have pretty reliable reference ages, and the only thing is depends on how long-lived tropical fish species are. So here we use, like at the end there in the deep learning network, we're using regression linear model, but we can definitely use classification too if it's a short-lived species. So yeah, I think it's a great tool to try on tropical fish.
Great. And then one final question from Jordan. You mentioned performing the analysis on board vessels in real time. What do you think it'll take to make that happen? What are the major hurdles right now?
Well, right now, well, first of all, pandemic. is one of the biggest hurdles. And then funding, because for this strategic initiative, we didn't get funded to explore fishing boats. So definitely, you know, as always, pandemic and funding, I guess. And yeah.
Great, thank you. So with that, we'll turn it over to Kimberly Sparling, who's going to be talking about autonomous vehicles, AI, and the blue economy. But we certainly can continue the questions and answers over in the Slack channel. Kimberly, go ahead.
Thanks. This is Kimberly, Cory, and Jack from Saildrone.
Yeah, we're going to do a little unconventional tag team presentation here for you guys. And we're going to tell you about some cool things we've been doing with sail drones recently. One technical moment. So for you guys who aren't familiar with sail drones are these really cool orange robots you can see pictured here. And I think they mainly came about as a platform for carrying ocean sensors. Sorry, we're having a hard time getting to our second slide. One moment. Okay, hopefully everybody can see our slide now. Somebody please stop me.
Great, we see that now.
Okay, great. So yeah, so sail drone is an awesome platform for carrying sensors to do collect data about the world's oceans on long duration missions all over the world. So some of the areas that we carry sensors to collect data in are ocean data. Many people around NOAA have interacted with our ocean and meteorological sensors. We're also starting to develop capabilities around ocean mapping, bathymetry, and hydrography sensing for both deep sea and shallow water mapping. And the application we're going to talk about today is maritime domain awareness, which is just kind of a fancy term for looking at what human activities are around you in the ocean. And just to give you an idea of when I say that we can do long missions and the platform is very durable, here are some pretty cool missions we've done over the past. On the top left, in particular, you can see that we did a circumnavigation of Antarctica. That's obviously one of the toughest places on Earth to be in the ocean for an extended period of time. And overall, we've done over 500,000 miles of sailing and put in over 35 years of sea days on sail drones. So it's a very reliable, dependable platform. So naturally, in order to augment all of these sensors and get sort of, especially to target those data sources which are too big to sort of fully analyze in real time, we wanted to bring machine learning and artificial intelligence to the drones. And for our first application, we've decided to target this maritime domain awareness area, basically to give sail drones the ability to see what vessel traffic is going on around them, both for their own safety and also to enable new missions that we can use to help observe and keep our oceans safe and healthy. So we set out on this project with the goal of detecting vessels during the daytime, so just limited to electro-optical visible spectrum cameras. And it's very important that what we do is we take a lot of images, which we can't possibly transmit back over satellite connections, and provide real-time information about them to enable short-sight decision-making. Some of our special constraints at Saildrone are that we have a very small power budget. The power is from solar and wind only to operate our vehicles. As we mentioned, there are very harsh operating conditions and long deployments. And because we want to be able to see a long ways, we need to stick whatever we build at the top of the wing, as you can see pictured on the right here. That's our camera system. That way you can see as far as possible, but because it's a sailing vessel, that means we need to minimize the weight of the package. So to accomplish these goals, both to bring AI to the sail drone and because we wanted to build a system for visual detection, we kind of packaged both the visual part, the cameras, and the AI together into that unit that we showed you that was on top of the wing there. At the heart of this is an embedded NVIDIA Jetson module with GPU and CPU capabilities, and we surround that with static 8-megapixel cameras that have a 360-degree field of view for statically and constantly monitoring all around the sail drone. And of course, the best way to do computer vision is with deep learning, artificial intelligence, which is what everybody is interested in. So we built a single-shot object detection architecture to look at each and every image. And then we layer that with a custom C++ sensor fusion algorithm, which tracks potential targets over time in individual images and associates that with AIS data. We have a few special domain challenges here. There's not a lot of publicly available data of nearly empty ocean or completely empty ocean scenes. So we built our own data set over time with all of those 35 years of sail drone time. We've collected a lot of pictures and we did our own annotation project on those. Still, most of those images are really just the empty ocean. So we've done a lot of work using models to provide feedback and active learning so we can figure out which images are most valuable for annotation. The targets we're looking at are super, super small. So we had to adjust the way we evaluate models. And we have to always run models on full resolution images. Otherwise, if you downscale them, you just kind of lose all the available information. And finally, because we are power constrained, I mean, tens of watts is just orders of magnitude smaller than what desktop GPUs use. We have to be very careful to use efficient architectures, pick very minimal architectures to start with, and even prune those further for even greater efficiency. And now Kim's going to tell you a little bit about the demonstration of how all this works.
Right. So what Cory just talked about is how we developed the capability. The first time we actually put that to the test was for a demonstration we did with the US Coast Guard last year. What you can see here on the map is the operating area we were within. It was just south of Oahu. We had 6 of our sail drone platforms deployed there with the camera system that we just described. And really what we were trying to focus and demonstrate on is how you can leverage this technology for illegal, unregulated, unreported fishing activities that might be happening in the Pacific region. Our objective was to alert users of any vessels in our op area within a specified time range within 1 nautical mile. During this demonstration, we actually worked with charter vessels to perform different vignettes focused on IUU fishing activities. And we were also happy to use the same system to identify any vessels of opportunity throughout the demonstration. So one of the vignettes that we focused on related to illegal fishing is monitoring restricted areas. So illegal fishing in marine protected areas or during closed areas during closed seasons depletes the fish stock and is something that we think you can sort of scale out using uncrewed technology. So what you can see here in the images is the plan to have the USVs hold station and run our tracking algorithm in real time to detect when vessels entered what we've denoted as the red zone in those images. We were successful doing this, and you can see an example of one of our charter vessels crossing into the red zone during this demonstration. Other activity that's commonly associated with illegal fishing is transshipment or the transfer of goods while at sea. This is often associated with laundering illegal catch, potentially related to transferring nefarious goods like humans and drugs. Really what we're trying to do here is use the algorithms on board to actually identify when 2 vessels are in frame and loitering. So we attempted to do this a couple times throughout the demonstration, and you can see here we were successful. Within the magenta box you can see here that is a secondary target, and within the green box here is the primary target. This was all identified using the artificial intelligence system that Cory just described. And finally, identifying, I would say that our technology is very good at identifying vessels within the imagery. And throughout this demonstration, really what we were also trying to focus on is sort of how do we identify behavior? So when you look at multiple frames together or behavior geographically from a vessel that we identified. So two well-known types of behavior are longline fishing and purseine fishing with pretty regular behavior types. So for longline fishing, slowing course or slowing speed, dropping a line, loitering, and then retrieving the line at a slower rate is something that we were able to identify using the system, as well as identifying circular patterns that are often associated with purseine fishing. So these are both examples of how you can specifically identify fishing behavior using the system.
Overall, this is a pretty successful mission. The biggest feedback we got from the Coast Guard was the need for other sensor modalities, specifically radar and passive acoustics. Radar gets you a lot better awareness of what the targets are doing. You can get a trajectory, you can get a sense of speed, and you can pick up on these patterns like fishing patterns, making it easier to identify behaviors. And you obviously can get increased range beyond what you get using just cameras and nighttime detections. Passive acoustics also complements this as well, because it can be used to detect smaller, faster vessels that you may not be able to see on radar or using the camera data. The radar work is actually done. We've implemented on our larger vessel right now, and passive acoustics is still a work in progress for us. To support these new sensors, we're actually building a somewhat larger vessel that's going to have a bit more power, and it's going to have a diesel backup engine. This engine is going to allow us to do these missions 24/7 in high latitude areas where you just don't have as much solar power as you would need to run these missions all the time. In addition, with a larger vessel, we're going to be upgrading the cameras and upgrading the basic compute and GPU packages just to take advantage of the state of the art. In terms of future missions, we're in discussion with some potential customers for another deployment. We would like this to be less of a test or a demonstration, but more of an actual application of the capabilities for actual missions that our customers want to do. In addition, we've got a variety of other missions we're focused on. To take a step back, we've got a robust sailing platform that's capable of onboard real-time machine inference, and that opens up a lot of capabilities for us. An obvious use case is environmental surveys for the wind farm industry. We could use the passive acoustics to do marine mammal detection using the ML, and the cameras for doing seabird detection and classification. We've prototyped some of these capabilities already with our existing image database. In addition, fish stock monitoring is a mission we actually run right now. We've considered augmenting our existing fish stock monitoring capabilities with some ML tools. That's about all the time we have. Thanks everyone for listening, and we're happy to take some questions.
Great, thanks very much for that that really engaging presentation. While Ali gets his presentation queued up and ready, let's go for one from Susan. Have you had challenges with security of your drones when operating in enforcement/surveillance environments?
Yeah, I would say that historically we've sort of mitigated that by avoiding those areas. I think that's sort of a problem that we will have to tackle eventually. Our mitigation strategy right now is to secure the data as quickly as possible and to identify who may be interfering with the vessel.
Great, thanks for that. There are a couple of other questions in the Slack channel that I'll direct people to, but in the interest of time, I'll turn it over to Ali, who's going to be talking about fish acoustic detection.
Hi, everyone. My name is Ali Ibrahim. I'm a research associate working at Florida Atlantic University. Our work now, today I will present fish acoustic detection algorithm research. Can you hear me?
Yes, we can.
Okay, sorry. So the outline of my presentation is, first of all, I will describe fish spawning aggregation, then I will go then to fish further our research, then Windows applications, and summary of our work. Fish spawning aggregation. Fish spawning aggregation is massive gathering of large number of fishes for the purpose of productions. Grouper and snapper and sea bass and other type of fishes species, they are commonly behave in this way. Fish spawning aggregation has been documented across 5 oceans and across 53 countries. Why is fish spawning aggregation is important? Fish spawning aggregation is important for the ecosystem health and fisheries and livelihood. For the documented fish spawning aggregation site, 52% of them are unknown, 26 from these known, 26% are decreasing, 40% are gone. Now, how we can monitor fish spawning aggregation? Depend on the condition of the locations. If it is suitable conditions, video camera, a video survey can be used. However, in the location that is poor visibility and challenging conditions, either sonar or passive acoustic monitoring will be used. So in my presentation, I will talk about passive acoustic monitoring. The four types of groupers that we will I will talk about the detection and classification, which are grouper family, right-handed grouper, NASA grouper, yellowfin groupers, and black groupers. These type of groupers, they are vocalized during spawning aggregations. You can see from this figure for the frequency range from each type of vocalization. For example, right-handed grouper, the frequency range from 30 to 45 hertz. NASA grouper from also around 30 to 45 hertz. However, black groupers from 20 to 100 to 200 hertz. In the below figures, two figures, there are 2 types of the yellowfin groupers, tunnel sound and bus train sound. Now we'll go to our research fishing. So we work on 2 ways: by using machine learning, conventional machine learning with handicraft features, and then we used deep learning approaches, and we compare both of them. For the conventional machine learning algorithm, we use, first of all, input sound. We pre-process sound, we remove noise from the sound, then we extract features from the sound, and then we train the classifier. This is in the training stage. In the testing stage, of course, any sound, we pre-process the sound, and then we extract the feature from the sound, and we use the trained model, and then we classify the sounds. Pre-processing stage, we used wavelet transform to denoise the signals. As you can see from in the left hand side, the right-hand grouper, spectrogram and original signal, and on the right-hand side, the noise signal with the noise spectrogram. Feature extractions. In the handicraft features, we use different methods as a feature extraction. One of them is MFCC feature, weighted MFCC features, multi-resolution acoustic features, and gamma tone GFCC features, and discrete wavelet transform features. These are features that we use with the machine learning algorithm. For the features method, we used gamma tone filter bank with the GFCC or weighted multi-resolution acoustic features, and we used male filter bank with the MFCC features. You can see here in the left side is MFCC feature extractions, which is divided the signal to the frames, and then apply for each frame we apply Fourier transform, and we applied male filter bank to the Fourier transform, and then logarithmic and discrete cosine transform to extract MFCC features. weighted MFCC features on the right side. We extract MFCC features and then the dynamic features, which is the first derivative and second derivative with weights, and add of them to produce weighted MFCC features. Weighted multi-resolution acoustic features. In this one, we pass the input sound signal to the gamma tone filter bank, which is this one on the left side. And then we calculate the parallelogram 20 per microsecond and 200 microsecond plus log, then applying windowing 5 by 5 and 11 by 11 and concatenate them, and then find the first derivative and second derivative to weight them and to calculate the dynamic features and concatenate them and to produce weighted multi-resolution acoustic features. These are the features that we used with the machine learning. For the classification stage in the machine learning algorithm, if we back for this one, we feature extraction, we used MFCC features, weighted MFCC features, multi-resolution acoustic features. And for a classification stage, we use different classifiers. The classifiers, KNN classifiers, support vector machine classifier, sparse classifier, and dictionary learning. These are machine learning approaches. Now, for the same problem, we used deep learning approach. Deep learning approach has achieved superior results, but the issue with the deep learning, finding suitable structure and architecture for this model is challenging. Which architecture is important, is suitable for the given problem? Is it DNN? Is it CNN? Is it RNN? Is it autoencoder? Which structure is suitable? How many hidden layers? How many nodes for which optimizer we use to train? So in this way, we propose a multimodal deep learning approach. Multimodal consists of R numbers of CNN, C numbers of D numbers of DNN, C number of CNN, R number of RNN, M numbers of stack autoencoders, and the parameter of all of these models are randomly generated, and then the output of each model fused. This is example, this is the proposed model. So first of all, we created different models, different CNN models, and different LSTM models, different deep neural network models, and different stack autoencoders models, and we impose the diversity of each of these models and in the model, and then we impose also diversity of the input, different input. We use discrete wavelet transform of the input signal. We use spectrograms image. We use scalograms image, and the output of each model, we fuse the output to create a classification result. This one is our proposed multimodal deep learning. Also, we use also transfer learning approach. Transfer learning approach, we used a classification model, which is trained by large data set, example such as ImageNet. We transfer knowledge from the old model by adding new layers, and we train by using our data set. These two models were used to classify grouper sounds, and then we have submodels. These submodels to classify types. For example, now right-handed grouper types. Right-handed grouper types. We have two types of right-handed groupers. This is type one of a right-handed grouper. If you can see, we zoom out the 0.428 second. This is the above the
2 minutes.
Okay.
2 minutes.
This is the right-handed groupers, and this is type 2. For right-handed sound type classification, we create also a sample of the stack autoencoders and we fuse the output of all of them. And you can see below each stack on the autoencoder consists of a random number of autoencoders. Dataset were used here in the Puerto Rico dataset unit in the Puerto Rico and United States Virgin Islands. These are results by using conventional machine learning. With different classifier, you can see weighted MFCC give us best result. Weighted MFCC with the sparse classifier give us best result. These are results also. Combined MFCC give us for 100 bear species. These are the experiment results by using transfer learning approach. From this result, we can see that VGG19 give us best result with the spectrogram. We input the data spectrogram to the transfer learning approach, and then we use scalograms. For our models, for the multimodal deep learning, we use different fusion techniques. If you can see in the right side, pattern net give us superior result. These are our model with our model with the human. This is the multimodal comparison detection algorithm of our model with the human. This is the comparison of our model with the handicraft features with the human. You can see that multimodal is aligned with the human detections. Also, we created Windows apps that can classify all type of the sound signals, and the user can choose the output of the classification either in app or export it as Excel file or export it as annotated video or create it for a folder of detected sounds. This is example of the output in app, the detections for each species and the time of detections. You can see this is the output as Excel file. This is the output as video. You can see this is the red hand. This is also the other output. You can see this is black grouper, NASA grouper.
Ali, if you can work on wrapping it up a little bit.
Okay. Yeah, this is so summary of our work. By considering handicraft features, sparse classifier with weighted MFCC achieve maximum classification accuracy. By using deep learning approach, CNN with spectrogram images, slightly better result than spectrogram with long short-term memory. However, considering multimodal deep learning approach, the most accurate performance is by using pattern net as a fusion. Future work increase number of species based on user input, develop a more user-friendly web app. Any questions?
Great, thanks, Ali. Really interesting. In the interest of time, I'm going to direct questions over to the Slack channel. There is one or two there right now. So Stacy, I think we're ready for your presentation, talking about AI as it relates to Arctic seals.
Great, thank you. I think Jordan is going to queue up my slides for me since I'm unable to get them working on my laptop remotely.
No problem. We'll bring those up right now.
Okay, great. Thank you so much. So good afternoon, everyone, and thank you for the opportunity to present our work today. Before I get started, I'd like to thank my collaborators, Yuval Boss and Aaron Moreland, for their contributions to the development of an annotation workflow and data set for Arctic seals in multispectral imagery. And my apologies, you're gonna have to hear next slide every time I need to advance, but thanks again to Jordan for queuing the slides up for me. So we fly instrument-based aerial surveys over ice seal habitat in the Bering, Chukchi, and Beaufort Seas in Alaska. An instrument-based survey means that we're not looking out the window searching for and recording animals as we see them, but we're collecting imagery during the survey that we then return with from the field and post-process to detect seals and get counts for abundance estimates. The advantages of the instrument-based survey are that the images we collect provide us with a permanent record of what we observed during our survey and the flexibility to try different approaches for detecting animals within our imagery, while also eliminating some of the elements that make in-flight detection challenging, such as observer fatigue, seal camouflaging, and weather conditions. From our survey, we return with tens of terabytes of color and thermal imagery, plus associated in-flight metadata about the location of the plane at the time the images were taken. Next slide. The seals can be hard to detect on a vast ice field, and species can be hard to differentiate at higher altitudes during an aerial survey. However, their warm bodies glow brightly against a cold sea ice when they are viewed with an infrared camera, and we can differentiate different species of seals in images collected by a color camera. During surveys, we collect simultaneous thermal and color imagery, which allows us to use information from both images to efficiently identify seals from our survey. Next slide. Our general workflow through the imagery and annotations is that the data are collected in the field through our aerial surveys. We've developed detection algorithms to identify hotspots in our thermal imagery and to classify species in our color imagery. Detection algorithms are either run in flight or back in the office, but regardless of the source, they generate tens of thousands of annotations, and then biologists review the imagery to create a final data set of seals. These annotations are then fed into two different channels, one for abundance estimates and one for bounding box revision and detection algorithm refinement. And further, we expect new annotations to be added to our data set as we refine our detection model and generate new annotations, but those sightings would not be included in our abundance estimates. The outputs from the detection algorithm jobs are CSV files for each flight and camera view during an aerial survey. And from our most recent survey, we had 29 flights and 3 different camera views with cameras pointing directly below the plane and off to the left and to the right to cover optimal habitat. So we have 87 different sets of detection outputs that need handling. And each detection output consists of 2 detection files, one for thermal hotspots and one for species ID and the color imagery. So the volume of annotations kind of pretty quickly gets unruly with the number of files that we're generating, and then also complicated by having multiple biologists reviewing these files. Next slide. So as this workflow has, back one. As this workflow has developed over time, we've invested efforts into developing an approach for managing our annotation data that works well for the data to feed into both abundance estimates and for further detection model refinement. And so today I'm going to focus on the efforts we've made in streamlining the processes here highlighted in red. Next slide. Our main objective was to develop a system and workflow for managing pipelines and resulting annotations generated from ice seal detection algorithm development and application that works with our survey data that's stored in our database. And we approached this effort in 4 different stages: outlining our objectives, identifying the technology to help us achieve our objectives, implementing the workflow, and evaluating our approach against our original objectives. And for the remainder of my presentation, I'll share details from each of these stages. Next slide. In the first stage of our efforts, we worked to identify the objectives that were most important for us to consider as we evaluated our technology options and implemented a workflow for managing our annotation data. I could talk for quite some time about each of these objectives, but I just want to highlight a few. Given the staff resources available to support this work, we knew we had to keep the system that we developed relatively maintainable, knowing technology is always changing, and to keep our solutions functional within our existing Postgres database ecosystem. We wanted to ensure that the improvements we made were not just one-off solutions, but tools that could be usable for the long term and across multiple projects. And we wanted to ensure the process was collaborative and version controlled. We further had specific objectives for handling the detection outputs, the processed annotations after biologist review, and tracking different phases of model development and application. Throughout this effort, Yuval and I worked very closely together to ensure that the solutions that we were each developing fit into the larger ecosystem of annotation management, and tried to make sure that the tools that we were creating worked as seamlessly as possible together. Next slide. In the next stage, we evaluated our different technology options and landed on a tool set that was compatible with existing tools, that was comfortable for program staff to use, and was easily maintainable. We had previously chosen Viame's ecosystem of annotation software for detection review, bounding box refinement, and species ID. We are collecting multispectral imagery, so it was really imperative to us that we had a tool that would allow us to view the color images, the thermal images, and eventually ultraviolet images simultaneously. We used GitHub for collaboration and version control. We chose Python and R as our primary programming languages for the development of custom tools and code. We're continuing to use our Postgres database that is housed on a virtual Linux machine managed by the Alaska Fisheries Science Center. And we use a Microsoft Access front-end application for program staff to interact with the database. We evaluated the cloud for some of our work, but ultimately decided to go with the tools that I've mentioned here, as moving to the cloud would have had some trickle-down effects on other data within our program, and would have resulted in a kind of initial startup time investment that was a little bit out of the time frame that we were working towards in this initial stage of the project. Next slide. So in this next stage, we implemented our workflow, and I'm going to caveat this by saying that some of these steps are still in progress and that this list is not exhaustive of all of the components that we've implemented in our workflow. But in the interest of time today, I want to highlight some of the work that we've completed and the direction that we're moving for managing our annotation. And I'll step through and share details for each of these efforts listed on the slides to come. So next slide. So first off, with as many CSV files as we're having generated with the detection algorithm outputs and using the Viame software, we knew we really needed a way to manage the files that was really organized, easy for staff to reference, and standardized for the sake of custom code developed as part of our workflow. So we developed a folder structure that can be applied to each batch of annotations. That includes several folders that need through which data can be moved throughout the structure while the annotation review is in progress. So that's folders that start with the numbers 1 through 3. And then also archive folders for the final annotation files that are generated. Those are the 2 folders that start with archive at the bottom. And then we've also created a corrections folder where, as we work through annotations, there may be things that we had considered data to be final, but find we need to make a modification to an existing annotation. Files can be moved to that corrections folder, updated, and then the update will be percolated to the database. Next slide. We identified several data management challenges running detection algorithms against our imagery using Viame. First, we had to run the detection algorithm against individual image lists manually. So if a job failed or had issue, it could be hours before such an issue was detected. And that's fine when it's a few files, but when we're dealing with 87 kind of different independent camera views, that just could be a lot of time lost as we're processing the data. And additionally, we didn't have a quick way then to track all of the details as the algorithms were being run on the images, and additional details regarding the processing job that we wanted to kind of maintain as part of our annotation metadata. So to remedy these challenges, you've all developed a custom tool that batch runs the detection algorithms on many image lists that are defined within a dataset manifest CSV file. Processing details for each job plus additional metadata are stored along with the output detection files, and then those outputs are ingested up into the database where the information can be tracked and queried. Next slide. Additionally, we've developed custom R code for tracking detection files through a number of our internal steps. These steps include creating image lists from data stored in the database, importing original detection files into the database, and moving those files automatically through the appropriate file folder structure that I shared before. Thanks. Importing reviewed annotations into the database and archiving the associated data, and applying corrections to the data when changes are needed. Next slide. For the staff who will be processing detection files and reviewing annotations, we developed an Access database front end that points to our Postgres database. From the main splash page, staff are able to access a number of forms, queries, and protocols for each project. As an example, by clicking on the View All Annotation Tracking Form button, staff are taken, next slide, to a new screen where they're able to see the details for each set of imagery that was processed using the detection algorithm, metadata about the processing job, and the status of processing steps assigned to each data set. For us, there were several benefits to using Postgres and Access for tracking this information. Among those being, first, that we have the capabilities to adjust and customize the information we are tracking and querying as needed. Secondly, staff in our program are already used to using Access front ends for other program database, so we wouldn't expect a steep learning curve beyond project-specific details. And finally, this was a pretty quick and simple solution for us to implement and should be easy for us to maintain, which was an important consideration when staff time is limited across a number of other projects. Next slide. And then the final implementation during this phase was really documenting our workflow. And we really felt like that was important to highlight here. Creating extensive documentation for all the processing steps within our workflow just ensures kind of a common knowledge among people who are using the workflow and the system and interacting with the data, and is often easily overlooked, I think, in the development of a system, and really wanted to highlight that was something that we really felt was an important component of implementing this workflow. Next slide. So in this final stage, it was important that we evaluated really how well our workflow addressed our initial objectives. I've added notes here in orange for most of the objectives that I showed at the beginning of my presentation. We've been able to make great progress on many of the more detailed objectives while keeping our overall objectives in mind. And while we still have some work to complete, both on elements that I've shared today and on a couple of our other objectives that are detailed here, we're at the stage of being able to apply this process to our most recent survey that took place in the spring. Next slide. And so just to wrap up, I wanted to share a few recommendations based on challenges and stumbling blocks that we've encountered along the way. First of all, plan early. This work is important to consider as you're really kind of investing into this machine learning approach, and the work is going to take longer than you probably expect. Evaluate the technology. There's a lot of different tools that are available, and finding the right tools for what you're interested in doing and what your needs are and what you have resources to be able to support is important consideration. And then just testing. It's going to take a lot of time to get something like this set up and think through all of your use cases early on so that you can evaluate the solutions as appropriate. So next slide. So with that, I'd just like to thank you again for the opportunity to present today, and thank you to everyone who's contributed to this project over the last year.
Great, thanks very much, Stacy. Micah, if you want to go ahead and queue up your slides. In the interest of time, we'll move on to your presentation. Remember, please do put questions or comments in the Slack channel. If we have time at the end of the session, we'll go ahead and recap questions for any of the panelists.
Great, yeah, can you hear me?
We can hear you, and just see that you're just moving into presentation mode.
Excellent. Yeah, I'll just start. Thank you so much for having me here today. I'm joining you from the land of the Coast Salish people, or Seattle, and we're going to be changing tack a little bit here to look at physics and physics of the global ocean. And within the climate system, the ocean is quite important because it has absorbed more than 90% of the heat gained by the planet from 1971 to 2010 here. And in this presentation, we're going to be looking specifically at the Atlantic thermohaline circulation. It's down here. It's one of those components of the climate system that are pretty sensitive to change and can even change quite rapidly in the future. Oh, excuse me. There we go. And this has even made it to popular culture here. There was a movie called The Day After Tomorrow that featured the Atlantic thermohaline circulation quite dramatically. But really the AMOC, or the Atlantic thermohaline overturning circulation, is really important for things like heat transport to Europe, atmospheric patterns, droughts, sea level hurricanes, you have it. And the circulation is very intricate. So here you can see that there are warm currents in the surface that bring heat up. Here there's the Gulf Stream current, or the current that sort of hugs the coast, the eastern coast of the US. And through a series of different things, it's brought across the Atlantic to the north, where it becomes cooler and sinks and returns in these deep blue currents here. And because of necessity, this is often represented just as one number. And you can see an example of this in the bottom here, where all of these numbers represent different models. Here we have different climate scenarios. And these climate scenarios and this data and these different models come from what we call the coupled model intercomparison project that I'm sure most of you are familiar with. It's now in its 6th phase. And this is a standardized experiment framework and a comprehensive climate simulation. So it's a great asset. It's a great tool to have available, or a resource to have available, but it also comes with some distinct difficulties. And that's that there are huge volumes of data. These are difficult to store, they're difficult to disseminate. So for me, for example, when I want to analyze this and understand the AMOC, I just don't have access to the data. I would need to really fully unpick the dynamics that I'm interested in. So this brings me to a bit of an overview here. There are 2 different tracks to this talk, because I know maybe not everyone is interested in large-scale ocean physics primarily. So I'm going to be talking about the North Atlantic circulation, but there's also an aspect of my talk that looks at just the machine learning aspect here, where I'm hoping that you might be able to see the algorithm that I'll be presenting as effectively a way of paying for the free lunch that we sometimes view machine learning as giving us, where what we're doing is combining domain knowledge with machine learning in a way that's trustworthy. And for me here, we've defined trustworthy as being both interpretable and explainable. So we've been hearing a little bit about the explainability methods here, and now we're going to be combining them with something also slightly different. And with this then, this is something that you can think of not just in an ocean physics sense, but also something, for example, like ocean trophodynamics, which I'm also thinking about a little bit. And the tracking global heating with ocean regimes, or THOR for short, is the algorithm. Everything's available freely on GitHub. We wrote it mainly in Python. It has 3 different components that we're going to be stepping through. The first one is looking at the full momentum equations in a realistic ocean model. And we used echo at 1 degree. And here we used equation transform to both make this, this more manageable, but also to enhance interpretability. And this is the interpretable step here, because then we can feed all this data, where if we depth integrate and take the curl, we wind up with what's called the barotropic vorticity equations. Here you can see 5 terms to the right. And within these 5 terms, we then ask, are there patterns? Are there overarching patterns within this data? And luckily, I guess for us, yes, there are. So we wound up with 6 different dynamical regimes, and these are balances within these dynamical forces that map very nicely onto onto different current structures that govern the AMOC system. And here you see the dynamical regimes on the surface and what they map onto. So with this now, we can then go on to step B here, the tracking part. And this is a supervised learning part. And for supervised learning, having data to test, train, and validate on is one of those limiting factors. And with the dynamical regimes here, we now have a giant set of labels. And because we've rooted this in a way where we know a lot about what's going on here, we know a lot about the dynamics, we can choose input features that we think are going to be able to represent those dynamics. And also, very importantly, we can choose input features that are available from the CMIP models. So here we chose wind stress curl, depth, and sea surface height. And we trained an ensemble MLP, so this is a neural network. And I want to pause slightly on the ensemble component of this, because this is quite interesting, and just note how we're doing this now. So now you can take a model of your choice, so a CMIP model, for example, extract the input data that you need, and then run this through the ensemble of multi-layer perceptron and take the mean of the predictions as your predicted class. And doing this as well, we also have access to these explainability tools that I mentioned before. And these are effectively a class of additive feature attributions, where one of them is called layer-wise relevance propagation that we've heard a little bit about in this workshop already and some of the other sessions. And this is where we take a trained network and use the fact that we've trained this and how the weights between the different nodes, and then we back propagate which nodes were helpful and which were actively unhelpful for the recognition of the different dynamical regimes. And you can see this here on the bottom, where we have the different dynamical regimes up here on the surface, on the top, excuse me, and the different input features here on the y-axis. And I've just sort of zoomed in on a few of them here, where you have the depth H and the wind stress curl. And for example, for the northwards Herdrupian regime, I chose this because it's a nice one for me. We know that the wind stress curl is supposed to be very important, and indeed we can see it as it's very red, but also that the bathymetry, or H, should be actively unhelpful. And I know this based on my physical understanding of the system. And indeed here, where we have this North Atlantic ridge running through, we see that the bathymetry is indeed actively unhelpful. So in that sense, with this knowledge that the machine learning application is actually finding something physical, I can go on with more confidence to try and see what is going to happen in a global heating scenario. So this is part C, where we take the GFDL ESM, or Earth System Model 4 for its historical 1% CO2 and 4 times abrupt CO2 scenario. So we're really hitting the climate system hard here. And the AMOC here is available. I have an estimate of the AMOC, or sort of the 2D field here. And the way we look at this is as a clockwise circulation here in red. And this weakens increasingly when we increase the climate forcing. And the mechanisms that we're interested in here that really show us why this is happening potentially, if we have access to the full 3D physics, is that you have a current. This current here along the east coast of the US is supposed to shift north. It's called the Gulf Stream. And the heat delivery here across is supposed to weaken. So here it's just sort of bending down a little bit. And the areas where deep waters are from, these waters that become cool, dense in return, move and they change their signatures. So if we now apply Thor to these 3 different scenarios, this is what we get. And if we just look at what's happening with these systems, looking at the different patterns and how they move, we see that the Gulf Stream that's here indeed moves north. The North Atlantic current doesn't reach as far north. So this blue strip doesn't even go up here. And this orange region shifts more towards the Labrador Sea. So we're effectively seeing exactly what we think we should be seeing if there is a weakening. But applying this to different CMIP models, here now you see 3 different ones. We can pick out differences between the models, although we know that the AMOC is weakening in most of them. But for example, in the UK ESM here, we see that the North Atlantic current doesn't change very much. So this is probably not something that's a source of this weakening. But for example, in the IPSL model, it does change a lot. So in this sense, we can start comparing the models, not just for exactly how much does the AMOC weaken, we can start to say something about why. So with that, I'm going to start my summary here and say that Thor really tries and strives for transparency in the sense of combining both interpretable and explainable AI. And using this, we're able to engineer a labeled data set to really make sure that we ground this in oceanographic theory and make sure that it's appropriate for climate analysis, because per definition there, we're working out of samples, so making sure that we're predicting these things for the right reasons is very important. And it's my hope that we can use these types of applications also across CMIP data, just also outside of the ocean, and also potentially as a blueprint for wider applications within the earth sciences for example, also within tropodynamics that of course are also relevant to fisheries. And this is a workshop, so I thought I'd also start with some, or end with some open questions in terms of machine learning methods in general, and that these are sometimes quite unreliable. We're only really scratching the surface of how to use them, but knowing that we can make them better and potentially even more appropriate for us as a field, I think is something that we as a field should have a conversation about, and potentially also go and talk to other machine learning practitioners about. And the other things that I want to highlight that are underway for Thor is that we're looking at different components of the ocean system as well, and climate, the Southern Ocean, and also an El Nino Southern Oscillation study where I want to highlight my student Zubru, who's now at Stanford. And also some co-development aspects here. Aparna Radhakrishnan is really spearheading trying to use Thor to potentially run within the Model Diagnostics Task Force. And the cloud was also mentioned briefly in the previous talk. This is something that we're also working on to try and democratize the access to both HPC here and access to Thor and the CMIP6 data. So we're hoping to get this available to people relatively soon, where if you're interested, you can take this code, you can run it, you can play with it, really with very low barrier to entry. And we're also, or personally, I'm also trying to do this again for high resolution, because I'm very interested in tying into NOAA observations and overall data assimilation as well. And with that, I really want to thank my wonderful collaborators, and again, invite you to go look at the code. You might not be interested in ocean dynamics in a larger scale, but I think there's a lot to learn and share as we're sort of, as a wider field, coming to grips with these exciting new methods. And I thought I'd end here with some references in case anyone wants to look things up.
Great, thanks, Micah. That was fascinating and, as always, a little scary. We do have a couple of questions coming in through the Slack channel. Since we are at the end of the session, I'll go ahead and open it up to questions for any of the speakers. Micah, from Tyler Christensen, how would better data access, for example, via the cloud, change your approach?
I guess the data access that I'm referring to is the access to different CMIP model outputs. So for Thor here, we used a series of different CMIP models, but if we had access to data from more models for the surface fields, we could of course look at more models and compare what's happening in different models. But if we had access to the full data sets for the full momentum equations, for example, for the different IPCC models, we could of course go in and really look at the detailed dynamics in a different way with more details, which would be really, really interesting. But currently with the IPCC data sharing limitations that are incredibly understandable because there is just a lot of data, one I think would struggle putting it all in the cloud, if that's part of the question as well.
It is great, thank you. And then one question back for Stacy Hardy from Matt Campbell. Do you have a plan to track model metadata and cross-validate against some standard to track changes that might take place to improve performance? He's worried that catchability might be shifting as he gets improved models in his program.
Sure. Yeah. And this is something that we've been thinking about as well. And it's hard to cover it all in a short amount of time. So our plan is to develop a system for kind of tracking which pipeline our imagery is being processed through. And that pipeline then is kind of archived each time that we make updates to it, so that we always have the ability to track which specific pipeline with thresholds and all of the little values that you tweak within these detection models, and have that information permanently available to us through kind of the link between the pipeline and the database.
Great, thanks very much. That's all the questions that I see in the Slack channel right now. We are right at the end of our allotted time. So I want to thank everyone for their participation and for the fabulous talks. Please do keep the questions and answers going through the Slack channel. And I'll turn it over to Jordan if there's anything else you'd like to say to close out the session or pitch later events.
There we go, a little bit of a delay. Yeah, I would reinforce or encourage people to attend the poster sessions and some of the plenaries and the final sessions tomorrow. I know folks get tired and burned out, but there will be just as many great presentations tomorrow as we've seen in these previous days. Thanks again for all of the emails back and forth and organizing, and really appreciate everybody's just fantastically interesting presentations. My brain is exhausted and spinning.
All right, excellent. Well, with that, I think we can close this session and head off to the posters.